morning. This is Calculus at Grand Rapids Community College, and it's Friday morning. We've just finished the topics that are going to be on the first test, but the last two sections had to do with finding work and finding the average value of a function. So I'd like to go over reviewing any of the homework that people had from those first. But we will have the test on Monday. Any questions from 6.4 first, all the work questions? Number 9. 9. Okay, so the questions were, we had this spring, and 2 joules of work is required to stretch the spring from its natural length of 30 centimeters to a length of 42 centimeters. Then they ask us how much work is needed to stretch the spring from 35 centimeters to 40 centimeters, and how far beyond its natural length will a force of 30 newtons keep the spring stretched. Okay, so with springs, we're assuming the force is equal to some constant, spring constant, times the displacement. But x is the displacement from its natural length. Okay, and then the integral from a to b of f of x dx is the work required to stretch from a to b. But again, a and b are these distances from its natural length. So the first thing is, natural length of 30 centimeters means that x is 0 at that point. Natural length of 42 centimeters means x is 12 if we're going to use centimeters at that point. Is that okay? Now actually, it should be 0.12 because a joule, since we use joules up here, a joule is a Newton meter. So let me write that again. That's 0.12 meters. X is 12 centimeters, which is 0.12 meters. Okay? So from this first statement, I know that 2 joules should equal the integral from 0 to 0.12 of kx dx. And then I use the J there, that's units. So for a second I'm going to step this off the side. So 2 is going to be equal to kx squared over 2, evaluated from 0 to 0.12. So 2 is going to be equal to k, and I put 0.12 times 0.12, I get 0.0144 divided by 2. Calculate out 0.0072 that is, and I'm going to divide. So K ends up being 2 divided by 0.0072. Which is approximately 277.8. Okay, so now we have our spring constant. Now I know for this particular spring, f of x is 277.8 times x. Okay, are we okay with that part? So when we go back this, how much work is needed to stretch this spring from 35 centimeters to 40 centimeters? Again, this is going to be x equal 0.05 meters and x equal 0.10 meters. Because a Newton meter is a joule, so I'm still working on that. So I have to convert that 30 is my natural length, so 35 is 5 centimeters, which is 0.05 meters. So this is going to be the integral from 0.05 to 0.10 of our 277.8 x dx. Still doing okay? Did we figure out what was going on? Did you?
I think I forgot x is 0 at 30.
Oh, so you were like using, did you convert to meters though? So you were doing like 0.3 to 0.42?
Yeah.
Okay. Does anybody want to see this finished out? Are we okay with this? The last one here, 30 newtons again is my force, and I know, so this is going to be 30 equals 277.8 times x, and then solve it for x. So it's something like so 0.108 meters, so 10, a little over 10 centimeters from its natural length, so out to about 40, a little almost 41 centimeters. But it said how far beyond, so this would be the answer to that. Okay. So another question. So that was the spring type question, where the force changed based on the position. And we're trying to figure out the work done. What's there another one? For asking out. Any ones with a rope or the bucket of water or any of the aquarium?
I don't know a question about 0.3. My answer, like they seemed like they rounded their answer a fair amount, and I got 103,673, and they said it was like 1.04 times 10 to the fifth.
You had 103.
103,673.
Yeah, so 104. If you rounded up that spot, it would be
like
the same.
Just rounded it.
Yeah, well, they are. So here's the engineer going to come out. So we have this tank full of water. notice these measurements here. How many, so mathematician 6 might as well be 6.000000 and as many zeros as you want. But in terms of engineers saying significant digits, we only have 1. So the real answer should have been 1 times whatever it was. He said it was 1.04. It really should be 1. They shouldn't go that far. Unless they measure, if they want to say this is 8.00 feet, then I have 3 decimal places, 3 significant figures worth of accuracy. Otherwise, I'm overstating how precise my answer is. Does that make sense?
Yeah.
So, not that we don't do it all the time. Like, we often say 1 mile is 5,280 feet. That one I can actually do. I would say it's 1.0 and go as many zeros as I want, because that's by definition. But then I'll say 1 mile is the same as 1.61 kilometers, and it's not really that. You see what I'm getting at? So, yeah. So the accuracy of the answer, I wouldn't expect you to have more significant figures than the numbers you were given in the problem.
But if we do,
I won't mark it wrong because it's not part of this problem, but I would, for those of you that are going into some applied field, be aware that you shouldn't give more accuracy than it's given. It's kind of like in another course, don't give more weight to a quote than the reliability of your source. So, like today, Mark McGuire's brother came out saying that he gave his brother steroids, HGH. And so the question is, well, how reliable is Mark McGuire's brother? It's that kind of thing, Well, yeah, he might be a rat, but the question is whether he's an honest in his statement or not, And you shouldn't give it more weight than it deserves. Okay, was there another, any other ones? I mean, these can often be tough for people. I just want to know if, did I hear 17? Is that what I heard out there? Okay. 17 is kind of a good one because it has all three parts almost in the same one. Although you can put them all together, I tend to think of them separately. So we have this leaky 10 kilogram bucket lifted from the ground to a height of 12 meters at a constant speed with a rope that weighs 0.8 kilograms per meter. Initially, the bucket contains 36 kilograms of water, but the water leaks out, and on the other side it tells me that it just finishes emptying. So it leaks out at a constant rate and finishes draining just as the bucket reaches the 12-meter level. So how much work gets to be done? So I have 3 things going on here. I'm lifting the bucket, I'm lifting a rope, and I'm lifting water that doesn't quite make it to the top. Okay, but part of the time I'm lifting it. So I tend to think of those 3 things separately. So the bucket, this is number 17. The bucket had a mass of 10 kilograms, and it was moved 12 meters, and acceleration due to gravity is 9.8. We'll stop at 9.8 meters per second squared. So to find the work done lifting the bucket, we're just going to multiply these 3 things because they're all constants. And I don't know what that comes out to be exactly. It's 1,176 joules. Now the rope is 0.8 kilograms per meter. So mass 0.8 kilograms per meter times my dx. So instead of 10 kilograms, which was, the bucket stayed the same mass all the way up. I'm not talking about the water. The bucket itself stayed the same mass all the way. The rope, parts of it are going to move farther than other parts of it. So I'm going to make slices. So if you picture the rope here going down, and at the bottom there's a bucket. I'm taking a little slice of this rope, and the mass of that slice is 0.8 kilograms per meter times my dx. And how far it gets lifted depends on what I define as x. So if I define x as from the top to the bottom, so x is going to be how much I lift it. Another typical value for x might be from the ground up. It's your choice, but if I did it from the ground up, then this would be 12 minus x. It doesn't really matter which way you go. So each slice is going to be lifted x meters, and the acceleration due to gravity is still 9.8 meters per second squared. But because my distance varies with respect to x, I have to write this in an integral. So 0 to 12, 0.8 times 9.8 is going to give me 7.84 out front, since it's a constant, times x dx. So again, this part, the 0.8 dx, represents the mass of that little slice. This x meters represents the distance. And then with the acceleration, mass times acceleration gives me the force. So these two together make the force, times distance is going to give me the work done. And that comes out to be x squared over 2, so it's 3.92 x squared, evaluated from 0 to 12. It's 564.48. Now, what I was just talking about, was precision here. When I get done with this, so during my calculations, I'm going to keep quite a few, 3 or 4 digits. But when I get done, I should only have 1. So my real answer at the end should only have 1, because they only gave me 0.8 kilograms here. 10 is really only 1. In scientific notation, this is 1.0. Is it 1.0 or is it 1? I can't tell. The way they wrote it, they didn't put a decimal point. I don't know if that's 2 significant figures or not. But this one's definitely 1. So when I get done, I should only have 1. But we'll calculate the way it is. So what do I have left to do? Kind of the harder part is the water. Now they left out something that's in all the other problems. They left out the shape of the bucket and how tall the bucket was and all of that. So what are we going to assume is that this is a pretty short bucket compared to the 12 meters that we're lifting it. So we're lifting it all up as it goes out. But if the bucket was really tall, like it was a 3-meter tall little narrow bucket, then the top part of the water is not being lifted as much as the bottom part of the water, and we have something going on that's slightly different than what they've said. But we're going to assume that all the water is at the bottom of the bucket, because they didn't give us enough information. So this is really going to be a high estimate, so to speak. And since we only have 1 significant figure, that's going to be good enough. So for the water, though, the mass is going to be tricky here. It did tell us it's 2 things are constant: the rate at which the bucket's lifted and the rate at which the water's going out. So I can come up with a mass as a function of how high the bucket is as a function of x. So when the mass is going to be 36, is that right? 36 kilograms. when X is at the bottom. So the way I chose my X, that's when X is 12. So how much water was in the bucket is 36 kilograms when the bucket's on the ground. And when the bucket makes it to the top, my mass, this is supposed to be not an X, that's a double S. The mass of my water is 0. So coming up with a linear function, because we have this constant rate of lifting and constant rate means constant slope. So mass is just going to be 3x. Y-intercept, vertical intercept is 0. Again, if you had chosen x to be from the ground up, then what would happen is these two numbers would be switched. It'd be 36 kilograms when x was 0 and 0 when x was 12. And this would look like negative 3x plus 36. Very similar. It's going to come out the same anyway. It's just a matter of how you set up your interval. Okay, so we're going to take it, integrate this from 0 to 12. And again, I have my 3, that's 9.8 meters per second squared. And like this last one, the distance lifted so this mass is more like the spring. I'm taking this mass and moving it. It's like the spring constant one. So it's just going to be the 3x times 9.8 dx. I'm not multiplying it by x because the water's not actually making it up. So 3x dx represents how far my incremental lift, how far I'm moving that much mass. Let's see if I can get this back to you. So there's a difference in how the rope and the spring constant, you think about it. With the rope, I'm taking each of these little slices and thinking how much does it weigh, and then my x represents how far I'm moving it. Whereas with the way the water is here and with the spring constant, x represents the position or an input into my force function. And so I don't need to multiply by an extra x when the force function itself already has, it varies with respect to it. Okay. So 9.8 times 3 is 29.4, and I get x squared over 2, and evaluate from 0 to 12. It's 2,100. Yeah, 2,116. So then I'm going to add that to 564, 48 plus 1176. So my total, I got 3857 joules, which is going to be rounded off to 4,000 joules. And don't use more significant, if you can remember, try not to use more significant figures in your answer than you're given in the problem. So the nice thing about that problem is it has all the different types. A fixed weight, fixed distance, where you just multiply. One where you're taking slices of weight and multiplying by distance. And one where the force actually varies with the position. Here, each of these slices has the same weight on my rope. But here, as I move the water up, it's changing weight. Again, that's the real difference between those two types of problems. You know, one of them, the force is changing as you move. The other one, the amount of force is the same. It's just how far you're moving. Okay. So what do you think? Is that okay? And somebody asked for 27. Is that what I heard? Brad? Okay, gas expanding in a cylinder with radius r. The pressure at any given time is a function of volume. So we're going to have to remember this. P, we're going to eventually write P as a function of volume. The force exerted by the gas on the piston. So we have a piston in a cylinder, little explosions with the gas that occur here, causing it to expand and push the piston that way. The product of the pressure, the force exerted by the gas on the piston is the product of the pressure and the area. So pi r squared, if the piston is smooth, the radius is the same, so that r is actually a constant, but it represents the cross-sectional area, the surface, or the surface of the piston with the gas on this side. We're assuming the walls of the pistons are immovable, and that the pressure is gonna push out on the piston head. And so the force is equal to the area times the pressure. Now we're supposed to show that the work done by the gas when the volume expands from volume 1 to volume 2 is given by this. Okay. So generally, what is this, 6.4, number 27. We have work done from A to B is f of x dx. So I could write the work as integral. Now we'll make like x1 be the initial position of my piston, and x2, I don't know if you remember seeing it down there, but down here at the bottom it labeled x as the displacement, how far over the piston head was from the end of the cylinder. And we said that the force here was given by pi r squared times p dx. Is that okay? So what I want to do is think of volume as a function of x. So if we were to look at, we're going to make a substitution. So this is sort of a review of section 5.5. Zoom in again. What's the volume of this cylinder right at that time? Well, it's pi r squared times the length x. Pi r squared x. Volume of cylinder general is pi r squared h, and h in this case is x. Okay. All right. So over here to the side, I'm thinking let v equal pi r squared x. So dv is pi r squared dx. And remember, when I substituted, to do a definite integral, I would change my limits, and put x1 in and figure out what the volume was at that point. So I could write here pi r squared x1 and pi r squared x2, And I would, except that in this problem, it told me to write V1 and V2 as my integration limits on the answer. I mean, but if you know, the note again, V1 is pi r squared x1 and V2 is pi r squared x2. I mean, I just don't, I'm not going to write that because it didn't want that as the answer. Okay, so pi r squared dx is my dv, and so I end up with the integral from v1 to v2 of p dv. Okay. So again, this was a nice little review of section 5.5. How, you know, what do you do with substitution? If you're switching your variables from one to another, it's another form of substitution. We used substitution last time in 5.5 to help us even do the integral. But here we're substituting because we want to change our variables. Instead of having the variable be how far displaced the piston is, x, I want the variable to be how much volume of gas there is in the cylinder, v. So. Okay. All right, how about questions on 6.5? Again, this is a review day generally, so you know, we might as well answer as many questions as we can since the test is Monday. How about questions on average value?
Could you just give the answer for number 22? Just like to see.
Where am I at here? Do I know the answer to 22 by looking at it? I can probably look it up here. 2/3. So the average velocity is 2/3 the maximum velocity. But if somebody wants me to do the problem, I can do the problem too.
Yeah. Would you mind doing it?
No? Okay. Yeah, here's a nice, for my fellows, was in the medical field. Nice little application. Although here he was, not anymore. The velocity of blood that flows in a blood vessel with radius r, capital R. So again, we're assuming the blood vessel radius isn't really changing here. And length L at a distance R. So you have lots of little cells of blood that we're talking about flowing through the blood vessel. Assuming the blood vessel's not changing as this is being pumped, you know, it's lowercase r represents how far from the center. So we're almost treating it like it's a tube, almost like it's that cylindrical piston, but we're having blood flow through it. And so lowercase r represents how far from the center it is, and uppercase R represents how far the radius of the tube itself. And here's the function. So P is the pressure difference between the ends. Eta here, this N looking like thing, is the viscosity of the blood. And L's the length, and the two R's we already talked about. This is the radius. So you can see that if a blood vessel is right next to the wall, it's not going anywhere. So as lowercase r approaches uppercase R, this velocity, r squared minus r squared, approaches 0. So velocity is very slow near the walls, fastest in the middle. Okay. just like you'd think if something was find the average velocity over the interval 0 to r compared to the average velocity with the maximum velocity. Okay, so the maximum velocity is going to occur when r is 0. So V max is just P capital R squared over 4 eta L. So I'll write that one down first. The average is going to be 1 over the length of my integral. Now my integral is going to go from 0 to r, capital R. So this is going to be r minus 0 of my function, p over 4 eta L, r squared minus lowercase r squared dr. So again, we're assuming that the pressure difference is staying constant, and eta and L, these are all constants. So these I'm going to pull out of my integral along with the 1 over r out here. So I have p over 4 capital R eta L times, and then I'm going to integrate these with respect to lowercase r, so I get an r squared, capital R squared lowercase r minus lowercase r cubed over 3, evaluated from lowercase r equals 0 to lowercase r equal uppercase r. So this first one, you're treating uppercase r as a constant, 5. The integral of 5 would be 5x. So the integral of capital R squared with respect to lowercase r is just r squared r. Yeah.
Alright, on the VAV you got 1 over r minus 0.
Yep.
How did you know that's 0? That that was going to be little r.
Little r represents the radius from the center of your vessel to the side. Maybe I should draw a picture here. It's always good to draw pictures. So again, we're sort of picturing this blood vessel as if it were a long tube, and the blood's flowing through here. Okay. Lowercase r. So let's picture one little tiny blood. That's a little blood cell. Okay. Lowercase r is the distance from the center of my tube out to where my little blood cell is.
Oh.
And then uppercase R is the radius of my blood vessel. Okay, so the smallest, again, this is the applied problem. Smallest r, lowercase r could be a 0 because you're going from the center out. Mathematicians somehow allow lowercase r to be negative. I have never figured that out quite exactly, but when we get into polar coordinates, we'll talk about, and spherical coordinates, I'll talk about that a little bit. But I guess it's a more free thinking. But is that okay now? Let me get the idea. So again, that's all right. And then L would have been the length of however long that particular blood vessel is. Okay. And really, in my mind, the radius of my blood vessel ought to vary as I go down the length of it. It doesn't seem like a blood vessel is uniform in radius. But over a short segment, this is probably true. The place where the clot might be here, we can maybe assume. So when I plug in uppercase R, I get 2/3 of R cubed. So it's, how should I put it? And that's where they asked you what the comparison would be. So V average. So I tried to factor out, knowing that V max was P capital R squared over 4 A to L, I tried to factor out the P, this thing here becomes R cubed times 2/3.
You knew that was the max just because you plugged in 0 for small r?
I did, but I was just using logic, but how would I find the maximum of a function?
Yeah.
How would we do that? Two things, right? You can go back to algebra and say, well, this is quadratic, and the maximum is going to occur at the vertex. And you could figure out what the vertex of that was. Or you could take how do we find maximums in Calc 1? Take this derivative of this thing, set it equal to 0. When I take the derivative of this term's going to go to 0, and I'm just going to get negative 2r times a constant equals 0, so lowercase r has to be 0. You want me to run through that? Are we okay? So I'm really fine with that. If you want to show it, that's great. Okay. All right. Any other ones?
I'd like to see 23.
43, did I say 23? 23? All right. They told us to go back to section 4.2. So I'm going to go back to 4.2 and write down the mean value theorem that they have in that section. There we go. Zoom in. So our function has to satisfy the following. It has to be continuous on the closed interval from A to B, differentiable on the open interval from A to B. The two endpoints are supposed to be, that's rolls, which is, I'm sorry, that's what you said. I heard, but delayed. I didn't want to open to it. Here we go, that's better. So first part was still the same. There is a number c in my interval such that the derivative at c is equal to the slope of the secant line from the two endpoints. Okay, that's the idea. So I'm going to write this part down. F prime of c equals, well, which one of these do we want to do? The first one. Okay. F prime of c equals f of b minus f of a over b minus a. So I should be able to say, this is the one, f prime of c equals b minus a, f of b, I keep doing another one, f of b minus f of a over b minus a. Alright, so in our case, I should be able to say f prime of x c equals f of b minus f of a over b minus a with a capital. I lost my cap somewhere. All right, now my a and b here are 0 and x. So is that what that's what we're trying to, I'm sorry, I'm on this point. I keep losing myself down here. Trying to prove the theorem they have here. here. Mean value theorem for integrals. I want to be able to say this. If f is continuous on AB, same thing, then f of c should equal 1 over b minus a times integral from a to b of f of x dx. All right, so b of f of x dx. Average. I want to say, I want to be able to come up with f of c equals 1 over b minus a. So go from a to b of x dx. Okay, I think we can do this. Okay. So, jeez, going back and forth. What's the derivative of f prime, capital F prime here? Yeah, so this side is going to be f of t. But when I plug in c, so f prime of x equals lowercase f of t, actually x, huh? It's the derivative of this, plugging in that endpoint. And so the f prime of c is going to be f of c, lowercase f of c. You okay with that? And then this, so I have it now as f of c is 1 over b minus a times f of b, capital F of b minus capital F of a. I'm going to go on to a different page here. So I'm moving this over here. F of c equals 1 over b minus a times, this should be the integral from 0 to b of f of t dt minus the integral from 0 to a of lowercase f of t dt. And if our function is continuous, I can put these integrals together and make it the integral from a to b of f of t dt. So we had to remember from last semester how to take the derivative with respect to the upper limit of an integral. And as you say, that's just plugging in the whatever the variable is into the function of your integrand. So it should have been x. F prime, capital F prime of x should be f of x. And then so capital F prime of c is just going to be f of c, lowercase f of c. And then remembering this idea. So when I put two integrals together, I can break two integrals up, put two integrals together. Is this part okay? So while the mean value theorem before told us that on some interval there's going to be a point where the slope of my tangent line is equal to the slope of the secant line between the endpoints, what this tells me is there's some point on my interval where the height of my function equals the average value of my function. So it's on the integration side. Okay. Is that okay? All right. Before I forget, I've told everybody, but I want to make sure you guys know the Problems Plus assignment for this time is pages 448 to 449 to 469 and 10. And I think I said that was going to be due Wednesday, but I think I'm going to make it due Friday, a week from today. Which would be, what is that going to be? The 30th? What day is it? The 30th. I want you to, the reason is I want you to have a day to ask questions, and in case you have any. So Wednesday you can ask me some questions about them, because Monday's a test. Okay. So let's see if we can summarize. So we still have a whole hour. Sure. Okay, so these are the 7 sections we've covered, and sort of a simple formula that, you know, might have to be tweaked a little bit depending on the application, depending on what we're doing for each of them. So we started out sort of as a review here, integrating and saying that the integral of a function from a to b is equal to the difference in its antiderivatives. But we switched the thought, almost like we just were talking about with the mean value theorem, and said the integral of the derivative equals the difference, the change in my function. So if I want to find, say, the change in distance, I would integrate velocity from a to b. If I want to find things like that. So this would be a rate of change, and it gives me the total change from a to b. 5.5 was the integration technique called substitution, and we just did one of those not too long ago. But it helps us do some integrals that we couldn't do earlier. And then chapter 6 were all these applications, finding the area between curves. So we integrate from a to b to subtract the functions. This one again might have to be tweaked. I'm assuming f is higher than g. If they cross over at any points, then you have to break your integral up. Which one's above the other? 6.2 was volumes by slices, and really there were 2 types of these. There were volumes where we had something like a pyramid, and we took the slices and we figured out a function a of x that gave us the area of each slice, and then we integrated that from the bottom to the top. And then we had ones that were we call volumes of revolution, where you take an area in the XY plane and you rotate it around an axis, like the x-axis or the y-axis or some other horizontal or vertical axis. In which case, if we use the washer, what I call the washer technique, washer being like a washer on a bolt, then we have the pi r squared idea. So this is pi times the larger radius squared minus the smaller radius squared. Where f and g, similar to what they were here, I'm assuming that f is always farther out from the axis of rotation than g is. Then we did the same kind of thing with volumes by shells, cylindrical shells. So I need 2 pi rh, so 2 pi, a function that represents the radius from the center axis of rotation, and a function represents the height of my shells from the axis of rotation, and that's doing volumes by shells. And we often compare these two. When was one easier than the other? And then the last two sections that we just had some homework on, work is force times distance, so work is the integral from displacement a and b from f of x dx. And again, as a subgroup, there's two types here. One where the amount of force is changing as I change my x position, and the other where the weight is the same, but how far I move it is changing. So that's not actually quite f of x dx. It might be, I don't know how to describe it. There's another function in some of those that represents how far it got moved. And then the last one was average value. So the average value of a function over an interval from a to b, if the function is continuous, is 1 over b minus a, interval from a to b of f of x dx. You can see there's a lot of similarities in what we're integrating here in these applications. Coming up with different integrands that allow us to have this calculus mean apply in a different way. So, is there anyone in particular you guys want to see?
Do one of the volumes by shells.
Okay. Let me grab one of those out of here. Okay. We'll just do. Maybe I'll do 15 here. The function's pretty straightforward, but we'll set it up. Find the volumes of solids obtained by rotating the region bounded by y equal x and y equal x squared around the following lines: x-axis, y-axis, and y equals 2. So we're going to look at those. Okay. So y equals x and y equals x squared. The bounded region is between x equals 0 and x equals 1. Well, this parabola goes up now forever, so there's no region bounded up to right, and off to the left, the same thing. They split away from each other. So this is the region I'm talking about. Now, if I'm going to do the x-axis first. Is that what it asked? Okay. I'm going to do the x-axis first. With shells, you make your slice parallel to the axis of revolution. And then we're going to spin that around. Guess I get to see that. So again, you can think of it as a napkin ring or something like that, you know. It's kind of as the way this one little slice looks. So again, to find that volume, it's 2 pi RH is what we're thinking. 2 pi times the integral. And my variable here, actually it's a different color than that. Because I made my slices parallel to the x-axis, my smaller side is a dy. The little differential side's a dy. So that means I have to have my functions, my radius, and so the radius here is just going to be y. That's my radius of rotation. How far is it from the x-axis out to my slice? And then I need a function representing the height. So in this case, it's the right end minus the left end, but these right now are written as y as a function of x. I'm integrating with respect to y, so I need x as a function of y. So this one I'm going to have to write x as y to the 1/2. And I'm taking the positive root because I'm in the first quadrant here. I don't need the left side of this parabola. So this is going to be y to the 1/2 minus y. That's how long that is right here. Right end minus left end. What do you think? The setup's the key. I don't think you guys are as worried about how to integrate that now that I got it. And what should my limits be here then? 0 to 1, right? The y value starts at 0 and goes up to 1 for my region. Okay? This was the the shell technique. Yeah.
Why 2 pi? I get confused.
Again, it's based on the thought that when I take and cut a can, so I take my little ring here, I'm going to draw it thicker here. Wish I could draw better. Okay, and and its radius out here is r, this is its height. You okay with that?
Yep.
And then the thickness here is dr. Okay, I'm going to take some tin snips and I am going to cut this right down the middle here, right down one side, and then flatten it out like we used to flatten out cans when we wanted to recycle them. And when I flatten it out now, as this is going to be is 2 pi r. That's the circumference of the circle. So the volume of this piece of tin then is 2 pi r h times dr. So, which is why our formula, since we're going to take these infinitesimal small ones, becomes 2 pi integral from a to b. And instead of r, I have a rho, because it depends on, it depends on where I'm at, how far out. If you think of almost like those Russian dolls, you think of this as a series of shells within shells. The ones with a bigger radius are going to have a larger circumference, and so this piece of tin is going to be bigger on the outside ones. So I have a function, it's going to be as a function of x. And then the height of them might change too, depending on, if you're looking like at this one here, some of these are longer, and as you get towards either end, it gets shorter. So that's the comparison there. 2 pi, instead of r, we have rho of x, instead of h, we have x, or y, depending on which our independent variable is. Okay. Now, if I were trying to do this by washers, the slice would be this way instead, with a dx, and then volume would be given by pi times 0 from 0 to 1 of the upper one squared minus the lower one squared, x squared minus x to the fourth. Dx. So the upper function is y equal x. So when I square that, I get x squared. The lower function is y equal x squared. So when I square that, I get x to the fourth.
Could you just set up the integral for number 22 on page 442? So,
442. So these ones are where we're taking and emptying tanks of water, assuming the tank was full to begin with. Now an interesting question is, when they say full with a tank, they probably don't mean the stem up there. So we're going to just, because they didn't give us anything about the radius of that, they just told us the length of that. So we're going to have horizontal slices and move them up. So did you want to have your variable start at the top, or you want to start at the center? What would you like to do? One of them makes it easier to describe how far you're moving it. The other one makes it easier to describe what the radius of the slice is going to be as a function of where you're at. You follow what I'm saying?
I think it's from radius.
From the center, from where that point is? Okay. So since it's vertical, I'm just going to use y to represent the position, how far down it is, and have y equals 0 be, put like a set of axes in right here. Okay. So the radius of my slice here, so the formula for my sphere is y squared plus x squared equals 3 squared. That's the formula for the circle, I should say. So x is going to be 9 minus y squared to the 1/2 power. Well, x squared is going to be 9 minus y squared. dy is going to be my thickness of my slice, and the area of my slice is going to be pi times x squared, which is going to be pi times 9 minus y squared. Okay. Now, how far each of these is going to be moved So if I think of this as a positive y-axis up here, this is going to be y equal 4. So how far each of these is going to be moved is 4 minus y.
How did you get the y equals 4 again?
If this is 0, 0, it's 3 up to the top of my tank, and one more up there. So I'm going to do the integral from y equals -3 to +3 of the volume, which is pi times 9 minus y squared dy times the density, which is 62.5 pounds per cubic foot. And I need my dy to be further to the right. And then I have to multiply by how far they got moved.
Could you do 2 times 0, 3?
Unfortunately, this part, yes. That, no.
But if you did it
Because the upper slices are moving not as far as the lower slices. There's symmetry in terms of the tank, but not in terms of how far they get moved.
Is that squared supposed to... Oh, no.
It's because the radius was squared. I didn't need the square root part. So like I said, I think this is a better choice for y. If we made, y equal here, so that your integral can go from 0 to 6, then this function becomes y minus 3 squared plus x squared equals 9 and 3 squared. And in here you end up with y minus 3 squared, which isn't all that bad, but I mean, you can still get it. Still ends up being the same, but it's just it makes this little piece a more complicated function.
See, say it one more time.
I could change the variable so that I would probably use a different variable, make it I don't know, z or something, and have it start up here at the top and go down. But then the radius of this would be like a shifted center of my circle. So you know how I used x squared plus y squared equals r squared here? It would be y minus x squared plus y minus k squared. And so I'd have a y minus 3 here to shift my center of my circle up. Does that make sense? Yeah, so you'd end up slightly different. it still ends up, and then the distance you would have to carry each slice would only be 1 plus y.
Just be wide, right?
Well, no, you still have the 1 extra meter there.
Oh,
Or,
right.
well, if you put y up there, then you can do that too. You can do that too. You can move it anywhere you want, really.
Then you have to you have to have x minus an h.
Yeah, there you go. Yeah. So, okay. So, that's another work one. Yeah. That's a good question. Yeah, you know what? I'm sorry. Thank you. And that change. This part should be changed. I was just reading what they gave us at the top of that. But yeah, this is actually not. I need 1,000. I need more than 1,000. I need 1,000 kilograms per meter squared per meter cubed. Excuse me, times 9.8 meters per second squared. Thank you very much. I always use this because I wrote it down from right above the problem. It told me that it weighs pounds per cubic foot, but you're right. The units are in meters, not feet. Good catch.
If it was in centimeters, you'd have 100 times 9.8. Or I mean,
Centimeters each. Cubic centimeters. There's 10. There's 1 million cubic centimeters in a cubic meter. So you have a little bit of a shift there. I mean, the limits would change to 300 and 300, but or it depends on what you want to do. Again, it all depends on how you want to write it up. But this will be different.
Is the 1,000, is that in the book?
Yeah, that was actually an earlier problem, 19.
Oh, okay.
But which is easier to remember?
Oh, the 1,000.
Yeah.
are we gonna? I mean, should we have
Metric
that
is nice that way, right?
Yeah.
So, with standard water, 1 gram is the mass of 1 cubic centimeter. 1 kilogram, 1,000 kilograms per cubic meter. It all works out pretty nice. Go ahead.
Should we have that memorized for the test?
No. I mean, if could you? Yeah, but ask me if you forget it. I'll just tell you. But I might not write it on a test. So I put it that. Is that okay? You understand what I'm saying? So I might not write it on the test, but you feel free to ask me and I'll tell you. Because it's one of those constants that you might as well learn. But if you can't, I'm not going to punish you. Just ask. So the punishment will be that you have to ask. All right. So how are we doing with this? All right. Let me do one more problem. We didn't do very many of these kinds of problems. So this curve is supposed to represent the rate at which students arrive at the cafeteria. So here in the morning, this is like some cafeteria for breakfast. It looks like the maximum occurs here right about 5 minutes after 7. A little bit more than 30 students per minute. Okay, so the units are students per minute on this side. Well, I guess it should be arrivals per minute because faculty eat there too. The thing is, though, that the cafeteria doesn't open up until 7. So here at 6:50 in the morning, the line starts to form. And then when it opens up at 7, they serve a rate of 20 people per minute. course at a larger university. Okay? I want to know, so let me put in a few things like that, all right? So I'm going to write these down. You might want to write this down then. So the cafeteria opens. It's at 7. They serve at a rate of 20 per minute. Okay, and here are some questions I want to know. How long is the line at 7 a.m. when they open? And I have one more here. Well, you know what? Instead of doing that, I'll do so I have how long is the line at 7 o'clock? When is the line longest? What time? That's what I'm asking there. How fast is the line growing at 7:10? If someone arrived right at 7, how long will they have to wait? And when does the line disappear? And then what was the average wait time from 7 for people that arrived from 7 to 7:20? Okay, so I'm going to put this back up here. And hopefully you guys can see that well enough to... Maybe I'll put some stars here at 7, just for you guys to be able to see these points. Feel free to share ideas with each other, you know. lots of talking going on.
I mean, are you looking for estimates?
Yeah, or just, well, again, most of the problems in the book seem to give you functions, but it's just as common in real life to have data. And so we either have maybe a graph that you're trying to estimate from, or a table of data that you're trying to get from. So do expect at least one of each of those types of problems. I don't want you to forget that. That you might have numbers, you might have a graph, and you might have some equation, some formula too. And yeah, estimate is fine. Nearest hundredth of a person. No, I'm kidding. So that red line I just drew is when the cafeteria opened up. Sorry.
Did you say something about how many students are served? Oh, 20.
20, yep. Okay, so much talking. I can hardly stand it. So, so what were some ideas you guys had? How would I find the first one? How long is the line at 7 o'clock? Well, again, the first section we have in this test talks about the integral representing the change. If you integrate the rate, you end up with a change in the output, a change in the function value. So if this is the arrival rate, then if I just figure out the integral of this function from 650 to 7 when they open, that should give me the total number of people in line. It should give me the difference between how many people were in line at 650 and how many people were in line at 7. Of course, there wasn't anybody in line at 650 according to this graph. So if you use a right triangle as an estimate, you end up with about 130 people. If you use point-by-point estimate, it gets a little higher because this is a little bit rounded up. So it's about 150 people, so somewhere in there, the line's about 130 to 150 people long. But essentially, you're trying to find the area of this right here. Did anybody get that? Is that what you guys thought? Anybody think that?
Yeah, that's fine.
Good. All right. Then when they open, that green line there represents the service rate. Serving at 20 people per minute. So they're still arriving faster than they're serving until this point. At that point, the rate at which arrivals are coming is less than the rate at which they're serving, and so up until that point, the line's getting longer. And at that, whatever that's about 7:16 or 7:17, somewhere in there, that's going to be the time when the line's the longest. Okay? And then how fast is the line growing at 7:10 is just reading the graph. That point looks like it's about 28, and they're serving 20 people, so this difference here is about 8. So about 8 people per minute is how fast the line is growing at 7:10. Okay. How are we doing with all these so far? So if I arrive at 7, we said the line was about 140 people. They're serving them at 20 people per minute. So 140 divided by 20 means about 7 minutes for the wait. There's 140 people in line. They're serving 20 per minute. So it takes about 7 minutes to get through.
But aren't there still more people coming after?
Yeah, but they're behind me. That doesn't affect how long it takes me to be served. And then finally, when does the line disappear? So if I were to call this area here, if I call that A1 and call this A2, those two areas represent the length of the longest line. And if you add them all up, I got about 260. Right. This area now, over here,
A2, what's the worst other?
right
Yeah.
there, it's cut off. It's the part that's above the service line. So again, this is like the area between two functions part of your test. How much area is up here. Okay. Now what I want is this area down here. I want to figure out when the area below the service line but above the arrival rate matches the sum of these two. So I'm going to cut it off on the right side when it gets to be about the same. And when I figured out the areas as best I could, I got right about here to where this area was the same as those two together. somewhere in there, 738, 737, somewhere in there. So if I were doing the integral, I'd have a 0. Because the area here that's below would match the areas of these two things above. And then average wait time from 7 o'clock to 7:20. Average wait time is going to be the average length of your line divided by the rate at which they serve. So you're going to figure out what's the average length of line between here and here. So it's 150, and what did I say? It ended up being over here was about 230. Add those two, divide by 2, so the average length of my line is about 190. Divide that by 20, you end up with about 9-10 minute wait on the average.